Here.
Recording has started.
So yesterday we talked about, well, the last couple of classes actually, we've talked about translating things into terms of these variables and even putting values in for the variables to evaluate an expression. Today we're going to start looking at what we can do to combine variables and when we combine them, when we can combine them. And what it comes down to is our same basic rules we've used for everything else. When we add or subtract, we need the same name. Two things that don't have the same name cannot be combined with addition or subtraction. With our algebraic numbers, that's the same variable. Here the name is the x. 2, we're going to combine counts like we do with all sorts of numbers. And our final step is we're going to keep the same name. So the basics is it looks like this. If we have 7x plus 4x, we combine, they have the same name, they're both x's. We combine the count, 7 plus 4 is 11, and we keep that same name of x. When we multiply or divide, we do not need the same name. Of course, our second step is always to combine counts no matter what the operation. And then we also combine the names. So for multiplication, if it were 7x times 4x, now these happen to have the same name, but we don't have to. We're going to combine the counts. 7 times 4 is 28, but we also combine the names. X times x is x squared. So let's look more at addition and subtraction here. We said 7x plus 4x is 11x. What if we had 6x plus 5y? What do we get? Well, those have different names, x's and y's. Just like adding 6 feet plus 5 pounds. Those are different units. We could not combine those. That would stay 6 feet and 5 pounds. Likewise, this stays 6x plus 5y. We cannot combine those with addition or subtraction. Even if it was just 9 plus 2x. Still, remember the names on this, even though it doesn't appear to have one, the name is there is really the place value of ones. That's 9 ones and 2 x's. Those are different names. We can't combine them with addition or subtraction. So that just simply stays 9 plus 2x. Well, what if we had 5x squared plus 3x? Well, it's still different names. It falls under the same category of having 5 square inches plus 3 inches. A square inch and an inch are very different units. An inch is a unit of length. Square inch is a unit of area. So because those are different units, we cannot combine them. Even though they're both inches, one is a square inch and the other is just an inch, we cannot combine those. The same is true over here. If our variables have different powers, they are different names. So 5x plus 3x is going to have to stay 5x plus 3x. So when we're looking at combining with addition and subtraction, we might have things like 7x plus 4y minus 3x plus 6y. Now, there are different names here. We have x's and y's, but it doesn't mean we're totally done. We can still combine the things that do have the same name. We have the 7x and the negative 3x that can be combined. Now, if you recall from earlier in the semester, dealing with those integers, the negatives, 7 plus negative 3, looking at the number line, this is 0. Positive 7 goes like that, plus a negative 3 goes like that. That result is a 4, because we end up at the 4. So 7 plus negative 3 is 4, and we keep the same name of x. We have the 4y and the 6y. 4 plus 6 is 10, and we keep the same name as y. We can have more than one name on a single count. It is possible to have 6xy. We have two different names. In order to combine them with anything else using addition or subtraction, the other number has to have exactly the same name. 6xy and 2xy do have the same name. I combine the count, 6 and 2 is 8, and I keep that same name of xy. What if it were 3xy and 7yx? This might look like different names, but remember we mentioned it briefly yesterday. Math grammar. It's appropriate, it's not wrong to have it listed as 7yx, but it's considered more appropriate to always list the variables in alphabetical order. Multiplication is one of those operations that we said was commutative. You can switch the orders, it doesn't change the value. This is really multiplication, 7 times y times x. I can switch that order to 7xy. Means the same thing. I have not changed any value there. So when I list it like that, these do have the same name. They are both xy, so we can combine the count. 3 plus 7 is 10, and we keep the same name, xy. Now, these algebraic numbers do have a lot of different possible names because we have not just letters, but all sorts of symbols that we can use for our variables, and we can combine them. Different combinations like the xy. We also can put powers on them. We might have 4x squared y plus 7xy squared. At first glance, these look like the same name. They both have an x and a y, and they both have a squared. But in this one, it's the x squared that's squared, and in this one, it's the y that's squared. Those are not the same name. 4x squared y plus 7xy squared is just that, 4x squared y plus 7xy squared, because they have different names. We can't combine them any further than that. Now, we are able to have multiple digit algebraic numbers, and the place values work just like our place values for whole numbers. For whole numbers, of course, this is the ones place, tens place, and hundreds place, but I'm going to write them like this, as powers of 10. We explored these a little bit the other day. 10 to the 0 is the ones place, 10 to the ones is the tens place, and so on. And in the first week of the semester, we looked at if I have a number like 347. I can write that out in long form or full form as 300s plus 4 10s plus 7 1s. Well, an alternative way of writing it out rather than using the words is to use the powers of 10 like I did up here in my place values. So 300s can be written as 3 times 10 squared, plus 4 10s can be just written as 4 times 10. 10 to the 1 is just 10, so I don't need to put that 1 there. Plus 7 1s would be 7 times 10 to the 0. Typically, we just put 7 there. We don't have to put times 10 to the 0 or times 1. But when we write our whole numbers out like that, it makes the structure of our algebraic numbers look way more familiar. I might have an algebraic number like 5x squared plus 2x plus 9. When I look at it here now, I see this is the x squared place, just like this was the 10 squared place. This is the x place, just like this is the 10s place. And this, of course, those are both the 1s places. This is just a number, but the place values are powers of x instead of powers of 10. With that in mind, I can take two algebraic numbers, like 5 squared plus 2x plus 9, and I can add them. Let's add that to 3x squared plus 5x plus 7. Now, in this case, the parentheses are not an enclosing symbol. They're not telling me to do anything first. They're just separating that these are two separate algebraic numbers. When I go to add those, I'm going to rewrite them just like I would any other whole number. So I do the 5x squared plus 2x plus 9. And remember, when we talked about adding and subtracting whole numbers, we talked about lining up the place values, lining up the columns. The same is true here. The 3x squared goes under the 5x squared. The 5x goes under the 2x. The 7 1s goes under the 9 1s. And we are adding down these columns. So we have 9 plus 7 is 16. The positive 16, so I put a plus in front of it. So two differences here between the algebraic numbers and the whole numbers. One is I always have to write them with the place values in there, so I have to put a plus or minus in front of each digit. That's a positive 16, so I had to put the plus there. Second is if this were a whole number, I'd be carrying if I hit 10. Algebraic numbers, we never carry. There's no way to convert a 1s into an x. Over here, then, we have 2x plus 5x is just 7x. Again, that's a positive 7x. I'm going to put a plus in front of it to link it to the next digit. 5x squared and 3x squared is 8x squared. Now, there's nothing else in front of it, so I don't have to put the plus in front of that. So my result is simply 8x squared plus 7x plus 16. One of the unique traits, we pointed out a couple of things that are different about our algebraic numbers from our whole numbers here. One of the unique traits about algebraic numbers that makes them way different than whole numbers is the way we handle negatives. Excuse me. If I have something like negative 239 as an integer, every digit of that number is either positive or negative. This is a negative 239, so that's a negative 2 hundreds plus a negative 3 tens plus a negative 9 ones. In an algebraic number, it is possible for each digit to be positive or negative on its own. We may have 7x squared, a negative 9x, and a positive 3. So you can see this digit is negative, or not. That digit is negative, or both the other digits are positive. With that in mind, those negatives make it more difficult to calculate with them. We might have 2x squared minus 11x plus 3 plus 4x squared plus 8x minus 9. Once again, we're going to rewrite this and line up the place values. So 2x squared minus 11x plus 3. We're going to put the 4x squared under the 2x squared, the positive 8x under the negative 11x, and the negative 9 ones with the positive 3 ones. And we are still adding here. 3 plus negative 9. Well, if we start at 0, positive 3 looks like that. Negative 9 goes the opposite direction, and it's longer, so we end up on the negative side. Arrows go opposite directions, so it's the difference between 3 and 9, which is 6. It's a negative 6. Negative 11 plus positive 8. Well, we start at 0. Negative 11 looks like that. Positive 8 goes the opposite direction, but it's shorter. So again, we end up on the negative side. It's the difference between the length of those vectors. The difference between 8 and 11 is 3. That's a negative 3x. 2x squared plus 4x squared is 6x squared. So that result becomes 6x squared minus 3x minus 6. Well, where it becomes more complicated is when we go to subtract. If you remember with these integers, something like negative 7 minus 4, we change that into adding the opposite. Negative 7 minus 4 became negative 7 plus the opposite of 4 was a negative 4. So now that it's addition, we could do the number line again. Negative 7, negative 4, that's negative 11. Or if we had 8 minus a negative 5. Again, we changed it to add the opposite. The 8 stayed the same. Subtracting a negative 5 became adding a positive 5. 8 plus 5 is just a 13. So when we go to subtract, we have to be particularly careful for those negatives. We might have something like 3x squared plus 11x minus 8 minus 5x squared minus 8x plus 3. So again, we're going to rewrite them, making sure we line up our columns. 3x squared plus 11x minus 8. 5x squared goes under the 3x squared. The negative 8x goes under the positive 11x. And the positive 3 ones goes under the negative 8 ones. And we are subtracting now between these. So negative 8 minus 3. Negative 8 minus 3 is negative 8 plus a negative 3. That's negative 8 and a negative 3 makes that negative 11. 11x minus negative 8x. Well, 11 minus a negative 8. That's 11 plus a positive 8. So that's a positive 19x. There's more digits in front of it, so we're going to have to put the plus in front of it. 3x squared minus 5x squared. Well, 3 minus 5 is a negative 2. And we keep the same name of x squared. So I had warned you at the beginning of the semester, those negatives come back to haunt us. Here's one of the places they do. Most of the mistakes I see with these are mistakes made dealing with the negatives. I'm going to have you try one in your notes. Let's have you do 4x squared minus 8x plus 2 minus 9x squared plus 5x minus 11. I'll give you a minute, then we'll go over that one. So we set this up, our 4x squared minus 8x plus 2. The 9x squared goes under the 4x squared. Positive 5x under the negative 8x. Negative 11 ones under the positive 2 ones. And we are subtracting. 2 minus negative 11 is 2 plus a positive 11. That's a positive 13. Negative 8x minus 5x. That's negative 8 minus 5, which is negative 8 plus a negative 5, which is a negative 13x. 4x squared minus 9x squared. Well, 4 minus 9 is a negative 5, so it's negative 5x squared. When we multiply or divide, we said we did not need the same name. We were simply going to combine the names. So we had 5x times 3x. Even though they do have the same name, we combine the counts. 5 times 3 is 15. But we also combine the names. Now we know x times x is x squared. But looking at what we learned yesterday, we know that this is really x to the 1 and x to the 1. And when we multiply exponents with the same base, both of these have a base of x, we add the powers. 1 plus 1 is 2. That's why that becomes an x squared. This were x to the third, 5x to the third times 7x to the fifth. Those are different names because those are different powers of x. X to the third and x to the fifth. While they're both x's, the different powers make them different names. We're still going to just combine counts. 5 times 7 is 35. And then also combine names. X to the third times x to the fifth. We add the powers is x to the eighth. If they have different names as in different variables, 8x times 2y, we combine the counts. 8 times 2 is 16. Then we also combine the names. X times y is xy. We could have multiple variables with them. We can have 6xy times 4x squared. Here again, we're going to combine the names. So we combine counts. 6 times 4 is 24. We combine names. Well, we have x times x squared. This is x to the 1 again, times x squared. So we have the same base. We combine the powers. We're multiplying, so we add. 1 plus 2 is 3. That's x to the third. And there's nothing to multiply the y by, so it just stays y. Now, when I say there's nothing to multiply the y by, I'm not implying 0. Anything times 0 would just be 0. I'm saying there's no other y's to combine it with, so it just stays y. I might have 3x to the third y squared times 5 x to the fifth y to the fourth. I'm still just going to combine counts. 3 times 5 is 15. And then combine each name. X to the third times x to the fifth. 3 plus 5 is 8. That's x to the eighth. Y squared times y to the fourth. 2 plus 4 is 6. That's y to the sixth. So I can combine each name separately. And again, I'm using those rules of powers that we talked about yesterday. Well, what if I have more than one digit in one of my numbers? What if I have something like 7x minus 5? That's a number with just 2 digits. It's not 2 separate numbers. It's a single number with 2 digits. It has the x digit and the ones digit. And I want to multiply that by 4. Well, the long way of doing this, the real way of doing it, just like we would with whole numbers, we write it out as long multiplication. Put the 7x minus 5 on top, times 4, And we start at the right and work our way back to the left. 4 times negative 5 is negative 20. 4 times 7x is 28x. So that's 28x minus 20. Most of you, if you took algebra, probably learned a shortcut for this called distributing. And distributing is nothing more than just a shortcut for this long multiplication. In order to avoid having to rewrite it and being able to just do it right in its own space like this, we distribute. So we take this number out front in front of the parentheses that we're multiplying by, and we take each digit inside the parentheses times that. 4 times 7x is 28x. 4 times negative 5 is negative 20. Notice we get the same result. This just took less space. So this is really the process that's going on, but to save time and space, we're going to do it this way with the distributing. Because as we get up into larger problems, we're going to have a lot of problems. It's way easier just to keep it in that own little section of the problem and not have to rewrite it off to the side. Now, of course, we can throw in more variables and more powers. We can have things like 7x to the third y times 5x to the fifth y to the third minus 2xy squared. We're going to take this 7x to the third y times 5x to the fifth y to the third. We combine the counts. 7 times 5 is 35. We combine the x's. X to the third times x to the fifth. 3 plus 5 is 8. That's x to the 8th. We combine y's. Y times y to the third. Well, remember, we think of that as y to the 1, so 1 plus 3 is 4. That's y to the 4th. Then we move on to the next digit, being careful that we keep that minus, that negative with it. That is 7x to the third y times a negative 2xy squared. So 7 times negative 2 is a negative 14. X to the third times x, well, you think of that as x to the 1. So 3 plus 1 is 4. That's x to the 4th. And y times y squared, 1 plus 2 is 3, y to the third. We can have more than 2 digits in there if we need to. We might have 3x to the third times 5x squared minus 7x plus 11. It's still just distributing. 3x to the third times 5x squared. 3 times 5 is 15. X to the third times x squared is x to the fifth. 3x to the third times a negative 7x. 3 times negative 7 is negative 21. X to the third times x is x to the fourth. And 3x to the third times 11. Well, 3 times 11 is a positive 33. And then it's the x to the third. There's nothing to combine with it. We might have 2 multiple digit numbers, like x plus 5 times 3x minus 7. Again, we could just write this off to the side and multiply this like we would any other number. Just like we did when we put our whole numbers in long form back in the first week. We can do the negative 7 times 5 is a negative 35. Negative 7 times x is a negative 7x. We move over to the 3x. 3x times 5 is a positive 15x. We're going to put that under the negative 7x because they're the same place value. 3x times x is 3x squared. We add those up. The negative 35, negative 7x and positive 15x is positive 8x. And 3x squared. That is the full form of multiplication for multiplying those two algebraic numbers. Now again, if you took algebra, you were taught a shortcut. And that shortcut used the acronym FOIL. F stood for first. You multiplied the first digit of each number. X times 3x was 3x squared. O stood for outside or outer. You multiplied the outside digits. X times negative 7 was negative 7x. I stood for inside or inner. You multiplied the inside digits. 5 times 3x was 15x. Now, since that's another x, I'm going to write that positive 15x underneath the negative 7x to help me remember to combine those. And L stood for last. I multiply the last digit of each number. 5 times negative 7 is a negative 35. And I combine. I've got the negative 35. Negative 7 and positive 15 is a positive 8x. And I have my 3x squared. Notice I get the same result. This FOIL process just takes up a lot less space. Now, personally, I like the long multiplication here because it makes sense. That's how we multiply other forms of numbers, whole numbers and everything else. The FOIL shortcut, it isn't a bad shortcut as long as you understand that all you're doing is taking this first digit, multiplying it by every digit in the second number, then taking the second digit and multiplying by every digit in the second number. If you depend on the letters first, outside, inside, last, it can get confusing when you run into a problem like this. (3x minus 7 times 2x squared minus 5x plus 4). FOIL doesn't work here because we have a middle digit in this one. You would have to have FOIMOMOIL. Well, we don't need to memorize a new acronym. We can just go ahead and use the concept. We know that we're going to take that first digit, the 3x, and multiply every digit in the second number. 3x times 2x squared, 3 times 2 is 6. X times x squared is x to the third. 3x times negative 5x, 3 times negative 5 is negative 15. X times x is x squared. 3x times 4, 3 times 4 is 12, and there's nothing to multiply the x, so that's just 12x. Then we move over to the next digit, the negative 7. Negative 7 times 2x squared is a negative 14 x squared. Notice I put it under the negative 15x squared so that I remember I can combine those. Those are both x squared. They have the same name or same place value. Negative 7 times negative 5x. Well, a negative times a negative is a positive. So negative 7 times negative 5 is a positive 35. And again, there's nothing to multiply the x. I put that under the 12x so that I can combine those later. And negative 7 times 4 is a negative 28. So now we can combine. I've got the negative 28. 12x and 35x are 47x. Negative 15x squared and negative 14x squared is a negative 29x squared. And my 6x to the third. We also have division. When we divide, we also do not need the same name. But typically what we're looking at is something like this. 8x squared divided by 2x. X to the third divided by 2x. X to the third and x are different names, but since I'm dividing, I don't need the same name. I'm just going to combine the names. 8 divided by 2 is 4. X to the third divided by x. We subtract the powers when we divide. We think of that as x to the 1. 3 minus 1 is 2, so that is x to the 2. If they had different names like 9x divided by 3y, we can technically still do it. It just gets a little ugly. 9 divided by 3 is 3. X divided by y is an x over y, x per y like that. Just like miles per hour. Miles divided by hour. Hours is miles per hour. Same type of thing. X per y like that. It has to have a fraction in it. We typically will not do this with our units in this class. But we could have something like 24 x to the fifth, y to the third, divided by 6 x squared, y squared. We combine the counts. 24 divided by 6 is 4. Then we combine each name. X to the fifth divided by x squared. Remember, we subtract powers. 5 minus 2 is 3, so that's x to the third. And y to the third divided by y squared. 3 minus 2 is 1, so that's y to the 1, or just y. We can have a multiple digit number divided by a single digit number. Just like having 846 divided by 2. We don't think of division this way because it typically doesn't divide out nice and neat like this. But we can do this. 8 divided by 2 is 4. 4 divided by 2 is 2. And 6 divided by 2 is 3. If each digit divides evenly by what we're dividing by, we can just divide each digit out and be done. And that's the way we're going to do it with our algebraic numbers. If I have, let's keep that on the page here, 12 x to the fifth minus 8x to the third plus 10x squared. If I'm dividing by 2x, I'm going to divide each digit. 12x to the fifth divided by 2x. 12 divided by 2 is 6. X to the fifth divided by x. Well, I think of that as x to the 1, so 5 minus 1 is 4. That's x to the fourth. Negative 8x to the third divided by 2x. Well, negative 8 divided by 2 is a negative 4. X to the third divided by x is x squared. 10x squared divided by 2x. Well, 10 divided by 2 is 5. X squared divided by x is just x. So we divide it out digit by digit. Well, these are some of those things that you only get good at by practicing. And along with them, I'm going to have you also practice those integers a little bit again. So our homework for today is out of the big book. We're going to start out with page 256 through 257. This is in the unit exercises. 1 through 75, the odd. That is just reviewing working with integers, the negative numbers. Then working with the variables, we got page 389 through 390. Exercise 13-2, 7 through 45, the odd. And page 392 through 393. I'll make those actually look like 9s here. Exercise 13-3, 7 through 45, the odd. And you may have noticed there's a quiz out there. It's quiz 11-12. It's posted in Blackboard that is due at noon tomorrow. Noon, October 23rd. Now for you guys, you have a Friday morning class, let me shut down the recording for this here. Tomorrow